Fancy 2 minutes. Got it. Okay. So first I'd like to thank the organizing committee for letting me come talk to you about wise brown dwarfs during your exoplanet meeting and spectroscopy of them with the Hubble Space Telescope. So I'd like to start really simply just to get us in the right reference frame. So we all know the classic spectral sequence of OBAFGKM. You can also think of this as a temperature or luminosity or a mass sequence with the most massive and most luminous and highest temperature objects are the O stars, and as you go to later and later spectral types, those properties decrease. What may be less familiar is that if you keep decreasing in temperature and mass and luminosity, you eventually get to the L spectral type, or L dwarfs, and then the T spectral type, T dwarfs, and then Y dwarfs. And Y dwarfs are what I'm going to be mostly talking about today. Okay, so this is a really nice graphic that shows the end of that sequence spectroscopically. And so we have our model spectra of a 3500 Kelvin object all the way down to a 400 Kelvin object, which is approximately Y0, and this is approximately M1. The model spectra are in black, and overplotted on each one is a single temperature black body at the same temperature as that model. And so if you look at the M dwarf, you can see that the black body and the model generally show a similar shape. But as you go to colder and colder temperatures, the models become distinctly non-Planckian, and that's because as different molecules, as you get colder and colder, different molecules will start to condense, and then you end up with these broad absorption features that pop up. And so for the L and T dwarfs, you get these really distinct features in the near-infrared, and so a lot of them are found in near-infrared surveys, such as 2MASS, Sloan, UKIDS, Dennis. But if you want to find the coldest objects, the near-infrared is a bad place to do it. There's not much happening over here. So enter the WISE telescope, which had two pass-bands specifically designed to find these cold type of objects. The first one is channel 1, I've labeled it down here, which coincides with this deep methane absorption feature where there's really not much flux at all. And channel 2, which coincides with this region that's relatively free of opacity at 4.5 microns. And so if you look at a WISE image of a really, really cold object, typically you'll only see it in channel 2. And so this is a WISE, or channel 3 is out at 12 microns. There's nothing there as well. So if you look at a blue, green, red, three-color image of these things, they turn up as these really beautiful bright green point sources. And so this is what a Y dwarf looks like in the WISE data. And there's not much else that occupies that color space, and so WISE was really adept at finding these things. To date, we have 23 confirmed Y dwarfs, 21 of which have been confirmed spectroscopically. The first one's in 2011, and this is how many there were in that reference. So there were 6 in the first one, and then these are all the references, discovery references since then, and how many were in each one. There are 2 objects that we have not confirmed spectroscopically. They're just too faint, found by the Penn State's own Kevin Luman. But they are undoubtedly really, really cold objects, and so I include them here for completeness. All of these objects, except for 1, maybe 2, if you want to be a stickler about it, were found using the WISE telescope. So WISE, when it comes to Y dwarfs, WISE is really the only game in town. Okay, so why study these? Why WISE? With really low temperatures and really small masses, and no bright host stars, so all you exoplanet people that have to look at really bright stars to try and find your planet, I'm sorry. These can really anchor our low temperature, high pressure models because we can actually observe them spectroscopically. And if with these low masses, if you actually found them orbiting a star, you call them a planet, not a brown dwarf. So these can really help us with our planetary models. So not only have we entered the era of directly imaged exoplanets, like HR8799, this is seen with LBT, or Beta Pig B from the Gemini Planet Imager, but we're also starting to get spectra of these objects. So this is an H-band spectrum with GPI. This is a combination of spectra from GPI and photometry from a few other places. And so when you get a spectrum, you want to find out the properties of these objects. You want to get the mass. You want to get the gravity. And so how do you do that? You compare to spectral models. And these are the same exact spectral models we use for brown dwarfs. And so anchoring them with brown dwarfs can really help us understand exoplanets. Okay. All right, so we use the WISE channels to detect these guys, but really if we want to characterize them, we want to look in the infrared, near infrared, and that's hard. So we go to space. So wide dwarfs are really, really faint, as you can see in the previous slide, with J magnitudes between 19 and 23, which is incredibly hard to do from the ground. So we use HST slitless grism spectroscopy, which has its own problems, which requires a lot of different reduction methods. If you want to talk to me about that later and why that's necessary, feel free to ask me. So this is our whole spectroscopic sample. The black are the spectra, the red are the spectral standards, just for reference. These are T-dwarfs. Obviously you can't read these, but these are T-dwarfs, Y-dwarfs, and really late Y-dwarfs over here. We use the G141 filter that gives us the J and H bands. We use the G102 filter to get the Y bands. And we have Y band spectra for maybe two-thirds of our sample. And so why do we want the Y band spectra? So why the Y band and why the Y? Right, it's getting complicated. So one of the main reasons is there's this really unique spectroscopic feature that shows up. So what I'm going to show here are some cloud sphere models from Simon et al. 2012, where I've labeled different molecular absorption bands and where they occur. So here's methane and water. And then these blue shaded regions are supposed to depict where the ammonia bands are. And so there's one in Y and there's a few over here. And so as we watch these models decrease in temperature, we'll see the spectra change. And I want to focus on what happens over here when you get to around 500 Kelvin. You start to see this deep absorption feature in the middle of the Y band. And so while ammonia may be affecting these other parts of the spectrum, it's kind of muddied up with what's happening with water and methane. So it's hard to distinguish what's actually happening over there with ammonia. And so we figured that the Y band would be a great place to look for ammonia in these low temperature objects. And so we look at all of our Y band spectra. These are all the spectra in black. The red is a T9 spectral standard just for comparison. And we don't see any obvious sign of this bifurcation of the Y band. And we think we have objects that are that cold. And so what's happening here? So what we think is happening is something called vertical mixing. So let's imagine we have two layers of a brown dwarf, an inner warmer layer and an outer colder layer. The inner warmer layer has more diatomic nitrogen, or not diatomic, molecular nitrogen than ammonia. In the outer layer, we have the other way around, we have more ammonia. And if we allow these things to mix around, usually that's okay if we're looking at models. Because that will just combine with molecular hydrogen and form ammonia and everything stays in equilibrium. However, if that mixing happens faster than that conversion, then we end up with less ammonia than we expect. And so that ammonia just doesn't show up because vertical mixing is too fast. And so we think that this might actually be explaining why we don't see ammonia in our study. Okay, so the last thing I'll mention was one of our standing issues. So this is a T8, T9, Y0, and Y1. The black are the spectra, the red are the model fits. And in general, they're not terrible, and let's just say, for argument's sake, that any discrepancies we can attribute to not having vertical mixing in our models. But our best fitting models in the near infrared don't match very well with the data we have out in the mid infrared. Okay, so we have data from Spitzer out here at 3.6 and 4.5 microns. And as you can see, the best fitting model for the T9, it actually matches up okay. For the T8, the observations are black. The model predicted is red. They're below for the T8 and the Y0, and for the Y1, we see this with almost all of our Y1s. It's underpredicted for the mid-infrared data, and we don't know why. We can't explain this yet. So we'll see that. So just to summarize, the Y-dwarfs are really good calibrators for our low-temperature models, which are really important for exoplanets, and Ys is been pretty much what it's supposed to be at finding them. Vertical mixing is probably what may need to be invoked to explain what we're seeing in the near infrared. Models are starting to trickle in. Tremblin et al. Just published a paper on including vertical mixing on a really coarse grid, but it seems to help mitigate the discrepancy. And then simultaneously fitting the near infrared and mid-infrared observations is still an issue that we're working on. Thanks.
Dynamical isolation, or are they ejected from protoplanetary disks?
We don't know for sure. But we think they're probably forming in isolation because there's no obvious place where they can. I mean, they're old, so they could drift really far in the amount of time in their time span, but we don't know for sure.
So if I recall well from brown dwarfs, they're always cool, right? So they go through the sequence.
That's correct.
Could the discrepancies be due to gravity, like some very massive brown dwarfs, also some less massive ones?
Sure, and so that's one. Well, we have different gravities. I mean, when we're fitting models, we usually just fit effective temperature and gravity and sedimentation efficiency, which is something else. But it's something I kind of swept under the rug is ages. I mean, these are probably really old because they're field and they're really low mass, but that could have an effect. But I think we're getting that with the model. That was your question.
I was going to ask, can you get any abundance information? Can you get any abundance as well?
We just want to detect it first, and then we'll try to so not maybe with JWST. Okay, thank you.